maybe back in August, I had given a similar webinar through SHI on serial debugging. So a little bit of an introduction to GDB and how you can use that to begin to debug your codes, as opposed to probably the naive way that people typically approach debugging, which is through print statements and so forth. So there was interest after that that possibly I could talk about extensions of using GDB when trying to approach parallel codes. And so that's really what I'm going to try to accomplish here today, is to give you guys a couple strategies that, GDB on the surface is not exactly ideal for parallel debugging, but there are a couple things that you can do with it with parallel execution programs. And so I'm going to touch on kind of some of those strategies that I might approach if I'm trying to use GDB to debug parallel programs. First, I wanted to kind of motivate the idea of why we want to understand parallel debugging. And here is a graph of 40 years of microprocessor data. And what we really want to focus on here is the frequency, which, as you can see, right, that's kind of the speed of the individual chips. Right around 2003, 2004, somewhere in that, it kind of leveled off, and chips no longer got faster and faster and faster. Instead, what happened is they started putting more and more cores, or in other words, giving you additional cores, additional processors on your chip in order to be able to do things in parallel. And so parallel computing kind of took off from there. And as a result, right, parallel computing, when we write codes in parallel, we also need to be able to find issues in them and debug them. So we also need strategies for debugging parallel programs. And so that's hopefully what we'll be able to touch on a little bit today. And so there are different types of parallel paradigms. There's MPI, message passing interface, where you basically have distributed memory. You split the memory into a bunch of different pieces, and each process kind of acts on the same set of data. There's threading, where you share memory, and you kind of typically you thread loops. So you would have you'd spawn a bunch of threads on one particular core, and that would generate a bunch of different actions that are working kind of in parallel to work through loops. And then there's GPUs and cloud and so forth as we get further and further down the rabbit hole there. As far as debugging tools, right, the typical one that you may be familiar with, and if you're not, you can go back and catch the introduction to GDB webinar that I originally gave. That's up on the SHI YouTube channel, as well as the slides, which are in the GitHub repo associated with the same repo here for the parallel one. You can go ahead and go back and look at that if you're interested in that or you're not familiar with it. But GDB is a free software, and you can use that to do debugging. And then there are commercial softwares like DDT. And DDT is typically available on supercomputing clusters and at some institutions, I would guess. And that will make it much easier to do parallel debugging. And at the end, I'll try to pull up DDT for an example, or at least to give you guys a little bit of experience of what DDT can do and how it kind of differs from the kind of low-level approaches we'll take with GDB and the examples that I'm going to work through here. So just to recap a little bit about GDB, GDB is a command line debugger. So everything's going to be executed on the command line through a terminal. And they do have some graphical interfaces that you can use at the same time, but typically I'm remoting in, so I'm going to be using mostly debugging on the terminal. And it supports C, C++, and Fortran, so the major codes there, as well as others. There are ways to use GDB with Python. I have a link here of Python discussing how to do that. Python itself has its own debugger called PDB, which is very similar in functionality to GDB. So if you primarily code in Python, similar commands that we use in GDB are going to be usable in PDB as well. And then, of course, the other debuggers that I mentioned, DDT, there are also other ones like TotalView. And if you use an IDE for coding, they usually come with some kind of graphical method for debugging as well. So that's just a recap of what GDB is for any of those out there who aren't familiar with it. Okay. All right, so when you're going to go ahead and try to debug a program with GDB or with anything else, the first thing you need to make sure you do is that you compile it with a -G debug flag. If you don't compile it with the debug flag, and this is something that you can go back and look at in the first webinar that I gave, you'll be able to load it up with GDB, but you won't be able to see the symbols as a result. So you need to make sure you compile with the debug flag there in order to be able to access the symbols and be able to proceed through the debugger. And when you're doing it with parallel programs, remember that if you're compiling a parallel program, you're going to need to link to your MPI library and any other programs that you're going to need. So make sure that you're linking explicitly to those. And then to launch GDB, and I'm going to walk through some examples here. So this is just kind of a recap. We'll go through these commands here. How do we launch with GDB? What are some of the major commands that we use typically when we run GDB programs for debugging and so forth? I've highlighted some of the major functions here, and there is a GDB reference card in the repo from the first webinar that has some information on some additional commands. So what I want to do today is focus mainly on MPI parallelization. Because that's typically what I have experience with. Most of my programs are MPI parallelized. So most of the examples that I'm going to do are going to use MPI for parallelization. And I'm going to talk to you guys a little bit about some debugging strategies that I approach when I have a parallel bug that I want to kind of understand. And so how can I use GDB in some way to allow me to approach it, or is it something that I need to kind of do with DDT on a cluster and so forth? So, and I'm going to try to walk you through some examples of using parallel, of debugging parallel programs with GDB to give you a feel for how you would actually apply these strategies in practice. And so if you happen to have been able to get GDB installed and were able to clone the repo and compile the programs, then you can go ahead and walk along through the examples with me. But this video will be posted on the YouTube channel. These slides are available on the GitHub. I'm available through email, which I'll post again at the end. And so if don't worry about necessarily being able to follow along. I'm going to try to walk you through it kind of interactively as we go through it. All right, so let me try to get right into the main work here, which is actually trying to do some parallel debugging. So if you just bear with me for a moment here while I pull everything up and try to manage my screen here. Okay, I want to share my desktop. Okay. So over here on the right, I've got two windows pulled up where I'm connected to a machine that has MPI capabilities, and I'm inside my SHI Webinar debugging GitHub repo. And inside of that, I'm going to go into my parallel debugging subfolder. And so the first example that I want to look at is the file npi integrate.cpp. So we can go ahead and open that up. It's a good idea to understand what our code is doing before we try to approach debugging it. So MPI integrate, as you can kind of imagine, is trying to do numerical integration. So it evaluates some function. And so the specific function I have written here in this eval function part of the code. And the function here is over on the left, and I've plotted it on the slide as well, so you can see what the function looks like. It's a piecewise defined function. And I want to try to approximate this integral numerically. And I'm going to use the midpoint rule in this MPI integrate.cpp. And I should get an integral of this function of 0.01. So let me go ahead and compile this. So my compile command, a couple important things here. So I'm using an Intel compiler, so that's why it's ICC. I want to be able to debug this, so I need to pass some GDB flag. So I need to make sure I pass the -G flag into my compiler. Just a quick, can everybody see this? Is the size of my text window here okay? Pooja, if you could let me know, does that look okay?
I mean, I could see it, but if you can blow it up, maybe a
Yeah,
size up.
let me make it a little bigger.
Thank you.
Okay, so here is my compile command. And like I said, you want to make sure that you include the -G flag anytime that you want to debug a program, right? That's going to allow GDB to recognize the symbols, which basically means the GDB is going to be able to understand the flow of the code so that it can give you feedback on variables and where you are and so forth. The important things that you need as you kind of walk through an interactive debugger. And then since it's an MPI program, I had to make sure that I linked to my MPI library and had the include path to my MPI header file in there. So I'm going to go ahead and copy this. I wrote a little script to generate that for me so that I could do this quickly here. And sometimes you might have a make file that'll do this. And so I'm going to go ahead and compile it, and that will create a MPI integrate executable. So you can see that just generated that. And if I go ahead and run that executable using MPI, so MPI run, I'm going to try to use 8 processors, and I'm going to run my program. And you can see that, as we would hope, right, since this is a debugging seminar, that we have some kind of problem that we need to resolve. So it prints out a message, error. You are trying to integrate between 0 and 1, but are attempting to evaluate at 1.005. So somehow we're trying to evaluate our function, right? So in the midpoint rule, you typically take you evaluate your function at the midpoint of the interval and multiply by the size of the interval. So somehow we're trying to integrate numerically past the upper bound of what we were interested in. And you can see here that it tells me that the problem is occurring on process 7. So the first strategy that I want to talk about today with debugging is that you can attach a GDB to a single process. So when you have a problem that's occurring in your parallel program, but it's occurring on a specific processor, so in this case, right, I'm having a problem occurring on process 7, then you can attach GDB directly to that processor, and then you can have control of that processor. Now, all the other processors that are running are still going to continue running and still handling their execution. Of course, they're going to get hung up at some place where they're waiting for the processor that you then have control of, that you've attached to, and now are controlling through GDB. They're going to, anytime they reach a blockage point where they need information from that processor, or they're waiting for that processor to make it to that point, they're going to get hung up at that point. But as soon as on our processor that we're controlling through GDB, as soon as we move through that point, all the other ones will continue to execute as normal. So that basically reduces it kind of like to a serial debugging problem, right? We have one process that we're interested in looking at, one processor, and we've attached GDB to it, and we can go ahead and work through that. So the question becomes, all right, well, how do we attach GDB to an already running simulation? Well, as we saw, when I tried to run MPI and run this program, it runs very quickly. So there's not enough time for me to get this program running and then attach GDB to the processor before it's finished, before it's gotten to the bug. There's not enough time that elapses between that. So I need to some way hang up the code on processor 7 so that it gives me enough time so that I can get GDB attached to that process and start working through it. And so that's really the first strategy that I want to talk about, is how do we hang up the code, and then how do we attach GDB to a specific process, verify that we're attached to that process, and then can proceed to debug from there. So let me go ahead and walk you through.
So there is a question.
Yeah, okay, so I see there's a quick question. Why don't I address that before I get into the example here? The question is it possible to attach GDB to the process on another computing node? So yes, you would need to be able to log into that computing node. Most supercomputers that I'm familiar with, when you request an allocation, so you request a set of computing nodes, whether through a batch script or interactive script, will let you then SSH directly onto that computing node. So if you know what the ID of that computing node is and you can SSH onto it, for the whatever processor, whatever node the process that you want to attach GDB to is on, you need to SSH onto that node, and then you can go ahead and figure out the process ID on that node and attach GDB to it. But you do have to do that on the specific node that you're on by SSHing onto that compute node from wherever you are. But like I said, most supercomputing allocations work in the way such that they give you the ability to SSH into those nodes when you have them reserved. So I hope that answers your question. I'm gonna go ahead and put this over here. Okay, so, all right, so what we were talking about was how do I attach GDB to this process? So the first thing I need to do is I need to hang up the code on process 7. So I'm gonna go ahead and open up my code, and I'm gonna put in a little bit. So first of all, it might be helpful to understand where that error is occurring, right? Anytime we see an error message like this, so I put in some error catching. So we see an error message, so we can go right to the point in the code, and this is a strategy that works in both serial and parallel, right? When you see what the error message is, you typically want to go to where that error message is, and then try to work your way backwards till you figure out what's generating that error message. So I'm getting an error message here. You are trying to integrate between 0 and 1. So if I open up MPI integrate and I look, I see on line 15 that that's where that error message is printed. And that error message then is part of the function, eval function. And eval function, I can see, is called on line 51. So on process 7, I'm going to want to hang up my code somewhere before line 51, so before the loop that calls 51, so before line 47 gets executed. And I actually already have kind of the framework for that put into the code here. So all I'm going to do is I'm going to introduce this variable, a bool here, of infinite loop, and I'm going to set it equal to true. And then on processor 7, so MPI rank will give me the processor of the specific, for each process that's running. So I know that when that rank is 7, so only on processor 7, am I going to get it stuck in the infinite loop. So all the other processors are going to continue to run past this point until they hit some kind of MPI, barrier. However, processor 7, because I've created an infinite loop in this while statement, is going to get stuck in that infinite loop, and it's going to stay there until I can come in. And one of the advantages of coming in with GDB is I can then change that variable, infinite loop, so that it gets out of that, and then I can go ahead and proceed from there. So by creating this infinite loop on processor 7, I'm able to hang up the code and give myself enough time to get GDB attached to the process so that I can begin debugging. So I'm going to go ahead and save that and recompile this. And now I'm going to go ahead and run it again on 8 processors. And this time I'm going to put an ampersand here because I'm going to do all this management here on one terminal. So I'm going to send these MPI processes to the background so that I get my prompt back so that I can go ahead and attach GDB on here as well. So I'm going to go ahead and let that run. And so you can see that's running in the background, and notice it didn't produce the error this time because we created an infinite loop on process 7 that it's now stuck on. So now I want to go ahead and attach GDB to process 7, but I need to know what the process ID associated with process 7 is. So in my slides here, I have the explanation for how you attach GDB to a running process. The first thing I need to do is identify the process ID. So I can use the Unix command, psax, and I can pass into that, I can pipe into that the name of the program that I'm trying to execute here in parallel. And since all of these 8 processors are on this same node, right? So I only have one prompt here. There's only one node on the machine that I'm working on. But on a supercomputer, right, you may have requested multiple nodes. So you'll only see the processors that are on that specific node if you execute this command on a compute node. But here, since I'm running, okay. Not sure why I have 2. So somehow I had a background process. So let me go ahead and kill that so that I only have 1. So somehow I had, well, I guess when I was testing the example, I somehow left one running in the background. So let me go ahead and do that so that this is cleaner. All right. So let me go ahead and execute the program again, and I'm going to re-execute that processor ID command. And so we can go ahead and see here now we've got 8 processors running. And MPI is going to number them in the order that the ranks are. So the lowest number process is going to be rank number 0, and the highest number process is going to be rank number 7, because I had 8 processors. So they're ID 0 to 7 in the way MPI handles it. So I want to attach GDB to process ID 20405. And so the way I do that is I call GDB, then I tell it the program name and the process ID of that program that I want to attach it to. And if I do that, you can see it comes in here. And hopefully you're a little familiar with some of the commands in GDB. So the frame command in GDB will tell me exactly where in the code I am at this moment. So you can see, sure enough, I'm stuck on line 38, which is where we put that infinite loop. So that should tell me that I'm on processor 7, but just in case, I can go ahead and print my rank. And sure enough, I am on processor 7 here. So just to verify that I had counted correctly, if I had a lot of processors there, I may have miscounted or have accidentally attached to the wrong one. I can verify that I'm on the processor where I know the error is occurring by looking at that rank variable. So now I've attached GDB to this process. I'm stuck at this infinite loop point. Now I want to go ahead and exit the infinite loop. So I use the GDB command set, and I set infinite loop to false. And now when I tell it next, it's able to successfully move out of that loop because I've reset the variable that was causing it to be stuck in that infinite loop to something that will allow it to exit. So now I have complete control over process 7 outside of the infinite loop, and I can go ahead and proceed and figure out what's causing the problem. So now what I'm going to do is I'm going to put a breakpoint in my code. So this is, so now I'm going to go back to some of the ideas that I talked about in the first webinar when I talked about serial debugging, which is putting in a breakpoint. So hopefully you guys are a little familiar with that idea. The basic idea of a breakpoint, if you're not, is I'm going to tell the code that I want it to stop execution at some point and give me back control in GDB so that I can examine things and try to understand better interactively what's going on in the code that's led it to this point. So I need to figure out what line I want to have it break on. So I'm going to go ahead and open up that file and have it break on the line where the error message gets printed. So if we recall, that was line number 15. So I'm going to tell it to break on line number 15. It says, all right, I put a breakpoint at MPI integrate.cpp line 15. Now, for those of you who have used GDB before, I have one file in my code here. So when I put break and just a line number, it's going to put the breakpoint at the file that it's currently executing in, that I currently am looking at. That's where it's going to put the breakpoint. So since I only had one file, I can put directly break 15. If I had multiple files, I would want to put the name of the file, integrate.cpp:15, in order to execute that breakpoint. But again, all of this is covered in my first webinar on serial debugging. So please, I refer you back to that if you'd like to look at that stuff. All right, so I put a breakpoint on line 15, and I'm going to go ahead and let the execution continue from this point. So I'm going to go ahead and type continue, and it's going to go ahead and run and then stop execution at line 15. So now that I'm at the point where execution has stopped, I'm going to go ahead and try to examine and figure out what's causing this error message to occur. So I can see here that these if statements are determined based on the value of position, right? So position, we can see, is the problem. Position is pointing to a point that's outside of 0 to 1, which it shouldn't be able to do because the right bound is 1 and the left bound is 0. So it should only be testing points between 0 and 1, since I'm doing a midpoint rule here. And so obviously 1.005 and the value of position is the problem. So that tells me immediately that I can go up to figure out what happened that called a val function with the wrong position location in it. So to do that, I'm going to do a backtrace. and backtrace tells me that a val function was called by MPI integrate.cpp line 51. So that gives me the stack, the list of functions and the order and the lines that executed that got me to the specific point that I'm in the execution of this file. I can see the whole history here. And so that tells me that if I go back up to frame 1, I can see where a val function was called. So I'm going to go to frame 1. So to do that, right, we talked about the frame command can show you where you are. Frame with a number will point you to that, will put you at that point in the stack, in the backtrace. So frame 1 will put me exactly at the point of line number 1 in my backtrace, MPI integrate.cpp line 51. And so I can see that the position, which was the problem, is the first argument here, which is midpoint. So if I go ahead and print midpoint, I should see 1.005, which in fact I do. So now I can come down here in my code and I can say, all right, so the problem here is the evaluation of midpoint. And now, since the purpose here is for me to kind of show you some strategies for parallel debugging, I don't want to get too caught up in the actual solutions to each one. So I'm going to go ahead at this point and leave it for an exercise for you guys. But the basic idea of what's wrong here is that the midpoint is calculated by the left boundary plus a local number of cells. And the problem is that the way I calculate local number of cells here introduces a bug, because when you unevenly distribute the global number of cells onto your processor, so 100 divided by 8 is 12.5. Since you can't have 12.5 cells on each processor, it has to do something, and I chose to round it. And that's where my problem occurred, because now I had too many cells on each processor, and so the last processor, I still have cells that are now going past the endpoint, because I'm adjusting my I'm adjusting my midpoint based on how many processors came before it. So the fix is going to be to correct the way local number of cells is done on the last processor, or to do a more involved fix, which would probably be a more robust and better way to handle it, of not actually trying to calculate local number of cells in this way. So I'm going to go ahead and stop there with this example and go ahead and move on to the next one. But just to recap the basic ideas of what I'm trying to show you as far as a debugging strategy here. The debugging strategy was that you had a parallel program and you were trying to run it, and you were observing an issue on a specific processor, or maybe 2 processors. And so you want to go into one of those processors and look at what is going on that led to the bug that you're doing. So in order to do that, you want to attach GDB to that process. And so you may need to put in a little bit of a hung block of code so that you can get enough time to find the process ID and attach GDB to it. So you put in a hung block of code. You figure out, using the process ID command, you figure out what processor number, what the process ID associated with that rank is, and then you execute GDB with that program and that process ID, and that will attach you directly to that process, at which point you can change the variable that has got you stuck in the infinite loop, and then you have control like you would in any kind of serial debugging, and you can go ahead and examine things as you would. The one downside of this, relative to serial debugging, is that in serial debugging, right, you can, when you find something, you can go ahead and restart the run from the beginning. That typically doesn't work with the MPI, so you do have to exit out of GDB, go ahead and restart it again and reattach GDB, since it'll now be a new set of processors, process IDs, and so forth. So that is one downside to this, and of course GDB is not really designed to be run with parallel programs, and so we are going to have some trade-offs when we try to use GDB in this way. Okay, so I'm going to go ahead and move on to the next example. Are there any questions here on this first example, the idea of attaching to a single process, before I do? Okay, so I don't see anything, but please don't hesitate to ask a question at any point if you do have one. So now I'm going to go ahead and move on to the next example here, and the next strategy. And so the next strategy is the idea to replicate your problem on a fewer number of processors. So let's say you have a big parallel program and you're trying to run it on, say, 96 processes. Now, if you've got a problem there, you certainly don't want to try to pull up GDB on each one of those processes. And try to manage them all manually. So instead, all right, let me try to motivate this a little better before I start talking about the specifics of it. So the example that I'm going to use here is MPI communication. So let's go ahead and open up MPI communication and see what that function is doing. So it says this file should create an array of size, grid size, and populate it with the processor ID. All right, and it will also create a buffer cell at the beginning and end of each array, which will contain information from its neighbors. So basically, it creates a very simple vector that populates it with the process ID, and then it does communications to its neighboring vectors and populates ghost cells on that vector from the neighbors. So let's go ahead and compile this. All right. So this is MPI com. And run it, and let's see what happens. So MPI com.cpp. All right, so let's say I want to run this program on 8 processes again. So I go to run it on 8 processes, and you can see, whoops, my fault, okay. I go to run it on 8 processes, and you can see that I got an error. Fatal error in MPI receive, invalid rank, MPI receive, invalid rank has value 8, must be non-negative and less than 8, bad termination. So we have some kind of error that occurred, but we don't know specifically what processor ID. If we were to dig into this error message and to look at the program a little bit, we may be able to isolate exactly what process ID this is occurring on, and then we could try doing it. But we'd find that if we did that we'd get a bug on a different processor and so forth. So we don't have one specific process that's causing the problem here. And so instead what we want to try to do is, instead of trying to manage 8 processes at the same time, right? We could theoretically attach GDB to all 8 processes, and we could try to manage them all individually. But that could be a lot of work. So instead what we're going to try to do is to reduce this, and 8 is even still manageable, but 96, 250, 10,000, if you're running very large programs, right? It's not feasible to attach GDB to that many processes and actually proceed by managing them and debugging them. So we want to try to reduce our problem to a smaller subset of processes and proceed by debugging there. So how can we do that? Well, in a lot of cases, it may just be as simple as just trying to run MPI with a smaller number of processors, right? Instead of 8, I'm going to try 2, because 2 is a much easier way to manage things. And you can see, sure enough, I get the same error when I run it with 2 processors as I get it with 8. So there's a good chance, not a guarantee, but there's a good chance then that if I fix the problem on the 2 processor problem, that it'll map to the 8 processor problem, and I won't have that error occurring on the 8 processor problem. So by reducing the size of my problem and allowing myself to run it on smaller number of processors, I can more easily manage GDB on, say, 2 processes, and then I can debug it, find the problem, and then that will fix not just the problem on the smaller number of processors, but on the larger number of processor problem as well. So you can't always just reduce the number of processors, right? Depending on what your program is doing, you may also need to manipulate what your program is, maybe the domain size or the grid resolution or the number of samples, et cetera, right? There might be something else that you need to reduce in order to make it feasibly run on a smaller subset of processors. But if you have like communication problems, like we seem to be having here, right? We have an MPI receive problem. If you have communication problems, it's more than likely that you can reduce the size of your problem and you'll still encounter whatever the bug is. So again, the goal here is just to reduce it to a small subset of processors such that we can then launch GDB on each one of those processes and manage them each individually. So let's talk about how we do that. How do we run a parallel program with GDB spawning on each processor? So in order to do that, I'm going to execute my MPI run command again. But instead of executing the program, I'm going to execute xterm -e and then GDB. And then if we had arguments for the program that we want to run in GDB, we need the --args command. And then you're going to have the program name, and then any kind of program args would go after it here. So I don't need the args command for this specific example, but the basic idea is I'm going to launch xterm on 2 processes attaching GDB, running GDB through MPI com. And so that's going to launch 2 processors. So you're going to need some kind of SHH X11 forwarding in order to be able to do that. So when I logged into this machine, I used -X so that I could do that X11 forwarding. So when I go ahead and launch that, it's going to take a minute because it has to launch these graphical windows here. But when I do that, I'm going to launch now 2 instances of xterm, so 2 terminal instances, each one executing GDB on an individual process. All right, come on. Oh, should launch them. I see that my X window launched, so it's trying to do. Okay, there we go. Just a little bit of a longer delay than expected. Okay, so as you can see, right, I launched MPI run 2 processes xterm. It spawned 2 xterm windows, each one with GDB, and these are then attached to 2 different processes. So I'm going to go ahead and close that window, and I'm going to open up my other window here so that I can pull up the code as well, so that we can talk about exactly where things are. So let me increase the size here. Nope. Well, sorry about that. I don't seem to be able to increase the size at the moment of the individual window. But hopefully you guys can see this well enough that you'll be able to follow along with what I'm doing here. But so I have 2 windows here. So what I'm going to do is I'm going to go ahead, and they're each now waiting for me to actually start the program. So it's just like when you launch a program with GDB in serial, right? It gets you to the GDB command prompt where you would then need to run the program, right? You'd launch the program with. Seem to have lost. Okay. You then need to launch the program with run to get it to start executing. That's the point that GDB is waiting at now after I launched it with MPI run np2 xterm. So now I have 2 processes that are right at the beginning, and they're ready to be managed in GDB. And I can manage them both individually like you would any kind of serial program. So I'm going to go ahead and put a breakpoint here right after line 24, where it is finished with the MPI kind of initialization stuff. So I'm going to put a breakpoint on line 32 in both of these windows, and I'm going to go ahead and run GDB. And so you can see now that both of them are broken at line 32. And the reason I did that is because I now want to print out the ID associated with each one of these processors. So I printed out processor 0 here and processor 1 here, so I can see that, all right, this one that it attached to, because the order that these windows pop up may not be the order that you think they are. So it's always good to check which window is associated with which rank in your MPI execution. And so we can do that by having a variable that returns the MPI rank and examining that in each window that we have open here in GDB. So basically this is kind of like attaching to 2 processes, right? Or to all, right? I'm attaching a GDB window to each one of these processes that are running so that I can manage them kind of in sync. And so you can see that, right, it's probably manageable for 2, 4, or maybe even 8 processors to kind of manage each one individually. But once you get to larger ones, you really need an alternative, and that's why I'm going to bring in the idea of DDT here at the end. So we have processor 0 and we have processor 1, so I like to lay it out so that it's kind of in chronological order there, so that I know. And if you recall back to the issue that we were encountering when we tried to run it with 8 processors and with 2 processors, we have a problem on MPI receive. So we're going to go ahead and go to the first MPI receive line, and we're going to put a breakpoint there, and we're going to see if we can figure out what's causing the problem. So we're going to put a breakpoint, and now I don't have to put a breakpoint in both of these processors, right? Each window is independent from the other. So I can do things in one window and let the other window run. So for instance, maybe I'll let this window continue, right? So that's going to continue. It's going to continue to run like when we had attached GDB to just one process, right? All the other ones were continuing their execution, and obviously they get hung at places where there's an MPI barrier. But so I can continue individual processes while I work on a specific one. I can break into those. I can put different breakpoints on different processors and so forth, so that I can. So I think I broke it, but so right, I can manage them in any way that I see fit for that individual processor. So that's one of the advantages here of attaching to each one, is that we might not need to do the same types of execution on each one, and so GDB allows us to manage that all. And so then I can kind of step through on, say, this second processor. So I know I want to put a breakpoint here on line 50. So I'm going to put a breakpoint on line 50. I'm going to go ahead and continue. And so we can see now that this one managed to get through all the way to line 53. And here I am stuck on the MPI receive command. And so I want to see if I can figure out why this MPI receive command is causing a problem. And so the thing I might do is examine some of the variables that are here. So for instance, this variable is the one that it's expecting to receive from. So I can go to print my ID +1, and I see, oh, it's trying to receive from processor 2. That was a mistake, right? The right processor, so this was designed to be periodic. So the right processor should receive through the right boundary periodically from the left. And so it's not going to be my ID +1 that's there, because I don't have a rank 2, right? I only have rank 0 and rank 1 because I only ran my MPI with 2 processes. So that's where my issue is coming up, and that's why if I were to continue, right, we could see that that line is the line that causes the problem, and it's because it's looking for rank 2, but rank 2 doesn't exist. All right, so we can go ahead and try to fix the problem associated with those neighbors, basically. What is the ID of the processor that's sending and receiving the message? And I already have this code ready here. So I can just create these neighbor IDs where I do a special thing on processor 0 and a special thing on processor n-1, so that it wraps around like a periodic boundary condition. So if I go ahead and do that and replace here my MPI send and receive commands, all right, so I'm going to go ahead and replace that, and then what I'm going to do is send to neighbor ID 0 and neighbor ID 1. I'm going to do the same thing in the second send command. And here it's +1 -1, so this should be neighbor ID 1, neighbor ID 0. So if I go ahead and do that, so just to recap why I'm doing this, right? The problem was occurring in the receive command on line 50. And the problem was because processor 2, which is rank 1, was trying to receive from its ID +1, which was process 2. But process 2 doesn't exist because I only ran with 2 processes, which has rank 0 and 1. And so that caused an issue. So instead what I did is I created a new variable called neighbor ID. And in neighbor ID, I populated what the correct neighbor should be for all processes, including the special cases of the edge cases, the 0 and the n-1 process ID, so that they could wrap around like a periodic boundary condition. All right, so I've corrected those issues in here. I can go ahead and recompile now. So I'm going to go ahead and exit out of my GDB sessions here. And I'm going to go ahead and recompile, which is in my other window. That's why I can't find it here. And then if I go ahead and run MPI com on 2 processes, I see now that I don't get the error message, but now I'm getting hung. So in the process of fixing that, I introduced some additional bug. So now I would want to go back in the same way, right? I could spawn GDB on these 2 processors, right? I'm going to keep iterating on the 2 process example until I resolve all those problems. Oh, never mind. I'm still running that in GDB. That's why it was taking so long. All right, so now if I run it on 2, you can see that it successfully ran. And it created these 2 text files, which are supposed to show me what the arrays on each one is, including the boundary cells. And so you can see that this looks like it may be correct, right? I have all 1s on processor 2, except for the 2 boundary cells, 1 from the left, and then 1 from the right, which really wrapped to 1 from the left, which was 0. So that looks reasonable. And how about 0? Oh, but 0 does not look right, right? I have 0s in the middle, but I should have 2 1s if it was acting correctly. So now, while I fixed the MPI bug, I have some issue about the message that I'm sending, or the way I'm handling the message, that's still causing an issue in that code. So I fixed the initial problem, but now I need to go back in and try to resolve what the new one is. But now it's happening on just 1 processor. So I could go ahead and attach just to that process like we did in the first example and proceed from there. And so again, not to get too hung up in the specific resolutions, I'm talking more about the strategies today. You can go ahead and treat that as on your own. And if you have any questions or run into any trouble about it, if you do happen to get a chance to work on it, go ahead and shoot me an email. So just to recap what that strategy was, and then I'm going to go ahead and move on to one other idea here, was that, right, the second strategy that I have for you for trying to debug things in parallel is to try to reduce your problem to a smaller number of processes and then attach GDB to each one of those processes and manage them each individually to track down the bugs. And that can especially help with communication problems, right? You can look at what is the message that's sent, what is the message that's received, am I sending to the wrong place with your codes getting hung, which is a common problem when you run MPI codes, and so forth, right? This can really help with that, figure out where it's getting hung, where it's seg faulting, et cetera, by running it on a small number of processors. But in order to be able to do this with GDB, you really need to be able to have a small subset of processes so that you can manage them all individually. And so that's really my second strategy. And those are really the 2 strategies that I have for you. There's, our goal with GDB and parallel is to really try to reduce it to serial-like situations. So attaching to a single process or replicating on fewer processors and then attaching GDB to each one. That's really the best ways to use GDB when you're trying to approach parallel problems. Now, one thing that I do want to caution you on that can come up in parallel programs that doesn't tend to come up in serial programs is the idea of a race condition. So a race condition, the idea behind a race condition is that the specific order of execution of your statements in parallel is causing the solution that you're observing or the bug that you're observing. And as soon as you change that order of operations via either debugging it, reducing the number of processors, or manually stepping through in a debugger, right? You're changing the order of execution relative to all the other processes. You can change the solution that you're getting. And as a result, that makes these very difficult to debug. And so I have a couple of recommendations for how to spot that condition. Basically, what typically happens is you're observing some sort of bug, and then you go in with a debugger, and you can't find the bug anymore. And that's a sign that it may be a race condition. It's not a guarantee that it's a race condition. There could be some other things going on. But it's a sign that there may be a race condition. Now, obviously, this really refers to deterministic codes, right? If you have a stochastic code where you've got random number generators, right, every time you run it, you're getting a different solution. So in those cases, when you're trying to debug things with random numbers, it's best to put specific seeds in so that you have turned it into a deterministic problem. But I have a deterministic code here, race bash, in this figure down here. And I'm going to go ahead and open up racethread.c, which is what race bash executes. And you can see that this is a very simple function that basically just, I see we have a comment. So if we look at this here, we can see that basically the goal of this function is just to sum a and basically print n, right? It should print whatever n is. So it should print 20 each time that we move through it. However, you can see that the last time it ran it, it ended up with 19. So there's obviously something happening where the specific order of execution is changing the fact, right? And so this is a pragma, so this is a threaded problem. And so the problem is that this is shared memory. And so in certain circumstances, you can get both threads to try to manipulate the variable at the same time, and you lose basically the variable there. And if we were to go in here in GDB, which I'll do just very briefly, if we were to go in here in GDB, so I'm going to set this to, say, 4 threads, and I'm going to go into and I'm going to execute this in GDB. Oh, I never compiled it. Let me go ahead and compile it. Again, make sure you put in the -G when you compile. So now if I go ahead and launch this in GDB here with 4 threads, and I go ahead and put a breakpoint on line 16, and I were to try to step through, right? Because the threads are all trying to share this and I'm manually kind of manipulating the threads, I'm not going to be able to observe the bug here, because each time I execute something, it's going to be able to do what it needs to do, and then the next the next thread is going to come in and manipulate it. So you got to be very careful about race conditions when you're dealing with MPI programs. And I want to just pull this up in GDB just to show you, because I haven't done any examples with OpenMP with threading here, just to give you 2 commands that GDB can use when it comes to threads. There's the info threads command, which will show you each of the threads that you're running with and where they are. And then there's the thread and then the ID number, which will allow you to individually switch between the threads. So you can use GDB to manage an OpenMP threaded program as long as it's on a reasonable number of threads. And you can manually go into each thread and examine what it's doing in case you're having problems there. I'm not going to go ahead and do any kind of debugging here. I just wanted to touch on that just to kind of give you a feel for how GDB can be used with threads. I have a link here to GDB's reference page on threads as well, so that you can go in and see some of the other commands that are there in case OpenMP is your main parallelization paradigm. So again, just to recap the point there, I just wanted to touch on the idea of a race condition, which can become very difficult when you're trying to debug, because the specific order of execution of the statements is dependent on the bug that you're trying to observe come up. And as soon as you go into GDB or something like that, you may know you're executing now in a different order, and so you're not going to see the same bug, and you may not see the bug at all. And so it can be very difficult, and so you have to be very cautious about that when you're trying to debug parallel programs. And so I just want to briefly, at the end here, try to pull up DDT for you and give you an example of what it can do and why it can be so much better for these. So if you just bear with me for one moment here while I pull this up. Okay, and I saw we had a yeah. So there's a question. Could you say something about debugging for GPU code? So I personally don't have any experience with that, but when I pull up DDT here, I'm going to show you that DDT is usually what's recommended for debugging GPU code. If you go out and you look at either the DDT website or you look for debugging GPU plus DDT, it'll give you some examples. And when I pull up the window to try to get it to pull up here, you'll see that there is an option for CUDA and so forth, and where you can try to get it to debug some types of GPU implementations. So let me go ahead and launch DDT here in the last couple minutes. Sorry, just bear with me. I didn't get a chance to pull this up at the beginning like I had intended. If there are any other questions, now is a great time for them. And Pooja, maybe you want to,
Yeah, so guys, please do fill out the feedback form before you leave. So I think Jeremy's going to do a DDT demo, and after that, he'll be here with us for another 10-15 minutes to answer any additional questions that you have. But I put in a link in the chat for the feedback form, so please do fill that out. Thank you.
Okay. And again, Pooja, if you want to just mention the slides will be up and the video.
Right. So the recording would be made available, and we'll send out a follow-up email with all that information. The slides are there in the GitHub repo. The link I've put in the chat again to Jeremy's GitHub repo. Also, we've put in his email just in case someone wants to get in touch with him regarding any questions.
So hopefully this won't take too long to load. I am doing this remotely, so it will be a little sluggish. But so basically DDT, it's by ARM Alinea, and it's a debugger which will make your life a lot easier in parallel. So if you do have access to it, unfortunately, since it's commercial software, it's typically only available on supercomputing clusters, or if you're lucky at your institution. But it will make your life a lot easier, but it is graphically, right? It's mostly a graphical interface. So you do have to have a way to connect in that way. You can do some stuff on the command line with it as well, but most of what you're going to want to do is through the graphical interface. So I can go ahead and pull it up here, and I can go ahead and tell it I want to run a program or attach to an already running program. So if I were running a program like we talked about attaching GDB to the process, we could use a DDT as well to attach to it. DDT is going to be able to do everything that GDB was able to do and more. I find GDB's nice because one, it's available everywhere. I can use it on my local machine, and two, it's command line so it doesn't have a lot of overhead. But for the parallel programs, it's just outmatched by these kinds of programs. So this is quite slow. So hopefully, for those of you that have patience, I'll go ahead and pull this up slowly here as we go through it, but it is going to be pretty sluggish as I walk through here. So I'll take questions now if anybody has them while I'm trying to get this up for you guys. And you can use is there a raise your hand option? Or just type it into the chat?
Yeah, so there is a raise your hand option. So at this point, you can turn your microphones on if you want to ask questions using the mic.
All right, how does DD compare to Intel Parallel Tools? I have not ever used Intel Parallel Tools, so I can't speak to that. I'm guessing that they're probably going to be pretty similar, right? Once you get into a debugger, there's only so much that you can do. I don't see any quick visualizations of it. So let me see if, since DDT is not cooperating here, let me see if I can get a couple pictures and just show you guys some of the key things. So you'd go ahead and launch. So here's what the run window would look like. So you would give it the application name. So you'd pass it the path to that. You'd give it the arguments. You'd tell it if you wanted MPI, how many processors that you want to be doing. You can see there's an option for OpenMP. There's an option for CUDA. There's an option for memory debugging. So you can go ahead and use DDT across all these different types of platforms, MPI, OpenMP, CUDA, for GPUs and so forth. And again, as I said, if you go out and just kind of do a Google search for debugging on GPUs, there are some explanations about how to kind of approach some things with DDT. Unfortunately, from my experience at this point, I don't have really any kind of GPU experience, so I can't really speak to that personally. So you go ahead and launch the application through here, and it would launch a window that looks kind of like, let's see if we can find, like this. All right. Okay, so it would launch something that looks like that.
Also, before you start, so I think there was some problem with the feedback form, so we've corrected that, and Sarah's put in the feedback form in the chat, so please fill that out. Thank you.
All right, so I'm going to go ahead and just use this window. I just want to talk about 2 or 3 quick things. So this is what the DDT window would look like when you're up in the debugger. So in GDB, we examine variables by using print and so forth. Here, right, whenever you're in a frame on the current line, you're given all the variables that are there, and you can go ahead and tell them that you want to examine them, and it'll move them down into this expression area. So you could examine some variables here, and you could keep them, and you'd always see them. It's kind of like a display in GDB. Or maybe you want to look at the variables that are all available in the local function. So you click on locals here, and you get a long list of them. So you have nice access to all of that. You have access to all your functions over here. And then you have all the processors up here. So it's to easily switch between the processors, right? It says you can just click on the individual process ID up here, and it'll switch you to that execution. And when you go ahead and create breakpoints, so if you've ever used an IDE and used a debugger in there, right, you kind of create breakpoints by clicking on lines. So you can go ahead and create a breakpoint. It'll create a breakpoint across all the processes. And then you can go in and tell it, maybe you don't want to do it on all the processes, you just want to do it on these specific processors or this range of processors. You have complete control over being able to do that. And so you can much quickly and all in the same window here manage all those different processors. So as you can imagine, GDB, right, you're having to do this individually on each window. And so for a small number of processes, that's viable. But for any kind of large scale program, hundreds of processors, your best bet is to try to do things here through DDT. And so if you do have access to a DDT through your supercomputer, if you're running on a supercomputer or through your institution, I do encourage you to pull it up and just kind of step through some programs that you're familiar with in it and get a feel for how it's going. And if you have any questions on it, you're more than welcome to send me an email, and I can try to work through some things with you. Because it is a very valuable tool. I mean, I think GDB is a great tool as well, but for parallel, there's really nothing that compares to things like these commercial softwares. Yeah, so that's really all I kind of wanted to touch on here for DDT, was just to give you a picture of what it is. And now that we've done a couple things in GDB, you have a feeling for kind of how it can make your life a little bit easier. Okay, so I see there's a question. In your demo code, there is only one global communicator. Will it be different when it has multiple communicators and even overlaps? Any tricks you can recommend? So yeah, multiple communicators, right? You're just adding more and more complication to what you're trying to do. So you need to be able to manage. You need to be able to manage what each communicator is doing and on each processor and so forth. So yeah, I mean, as long as you're aware of kind of, I mean, the best thing to do in those kind of cases is to kind of understand what the various communicators are doing and so forth, right? And which one is acting in certain situations, so that you know which way to examine things, you know where to put breakpoints and so forth. But as far as anything else besides that, it's really about kind of having a good feel for what your code is doing when you go ahead and step into the debugger. And sometimes stepping through a code that's running in a debugger, just so that you're able to get a better feel for exactly what it's doing, can be a very, very helpful learning experience. So I don't have any. I understand that probably doesn't answer your question very well, but the basic idea is just try to understand better what your code is doing, and that may help you a little bit in those kinds of situations. So just to summarize here, the slides, I have a link to that, and the video of the webinar, I have a link to that, and my email address here. Feel free to email me at any time if you have any questions about any of the examples I did, or any questions about debugging in serial or parallel. And again, if you go to the YouTube channel, there's my serial debugger video as well. And so that's really all I have for you. I hope that I was able to answer your questions to the best of my ability. If there are any other questions, I'm going to stick around for a few more minutes, and we can address any of them then. All right, well, thanks, guys.
Well, thank you so much, Jeremy. And yes, guys, please, I've put in the link for the slides in the chat, and there's obviously feedback form in the chat, so do fill that out. And thank you so much for attending.